All right, so we're looking on page 10 of your unit handout. We're going to be starting today with the first introduction to logarithms. Understanding logarithms is going to eventually lead to a procedure where you can solve those exponential equations like the ones that Zebby had asked about that was quite difficult, challenging in terms of trying to get the right window setting. Liam correctly pointed out to me that I was right when I said you have to have the right domain window settings for your calculator to find the point of intersection. And I was assuming that since I was getting an error when I did it, that we had to see the y coordinate as well. But since in retrospect the answer was like 14 point something, I don't know what it was, when I set up my window settings I only went 0 to 10. So I was assuming that it was intersecting someplace in that domain of 0 to 10. It turned out that had I just gone to 20, the calculator would have been able to find it. But regardless, using logarithms to solve that equation algebraically is going to be a lot easier, I think. Maybe, well, it's not easier necessarily in an algebraic sense because you're going to have to learn how to do algebra with logarithms, but easier in terms of you'll know exactly what you need to do. Okay, you'll have a series of steps that you can follow. So today we're going to be comparing logarithmic and exponential functions as being the inverses of one another. We have to be able to translate a logarithmic equation or expression into an exponential equation or expression and vice versa. And the word translate here is probably the best word that I can use to describe what's going on here. It's like speaking two different languages. You know, if I say bonjour and you're somewhat bilingual in terms of our two national languages, you understand that means hello. Am I right? Is that correct? Okay. Even though you might be thinking in French or thinking in English, you're able to translate bonjour to hello and hello to bonjour. And then we're going to be evaluating logarithmic expressions. So to begin with, one of the most important ideas behind logarithms is that a logarithmic function is the inverse of an exponential function. And that's why we studied exponential functions before we got to this stage of the game. Remember this goes back to, I think, chapter 1 in unit 1. That you learned what an inverse of a function is. An inverse of a function is the result that you get when you switch all of the x and y coordinates on the graph. And that means it's the result of switching the x and y in the equation. As an illustration, and I don't believe this is in your notes, but I've just thrown it up here, if I gave you y equals 2x minus 6, and I said, well, what is the inverse? And you need to follow along carefully here. Don't worry about your calculator or anything else right now. And I said to you, what is the inverse of that? Well, I swap out x and y. So if I have y equals 2x minus 6, the inverse is x equals 2y minus 6. We've switched x and y. The only problem is we don't like to write functions as x equals. So what we do is we rearrange for y. And rearranging this for y requires math that is the math that you need to rearrange this for y. You've learned so long ago, you probably don't even realize that you were taught it. It just becomes natural. I'm going to add 6 to both sides and divide everything by 2. Right? We've got to move the 6 over and divide everything by 2 to get y by itself. And you end up with y equals 1/2 x plus 3. And the mathematics involved in rearranging that linear equation for y is pretty simple. But that's the inverse. Now, on the other hand, if I gave you y equals x squared and I said, what is the inverse? The inverse is x equals y squared. And you know what? The math you need to rearrange that for y, you didn't learn till last year. Because before last year, you might have said, oh, y equals root x. And if you wrote y equals root x in Math 20, I would say, y is not equal to root x. Whenever you take the square root of something, you need to introduce the concept of plus or minus. So in order to communicate the mathematical idea of what y is equal to in this function after we switch x and y, and by the way, it's no longer a function because it will fail the vertical line test. In order for you to be able to communicate on paper what y is, you had to be taught some new symbols. You already knew about a square root, but somebody came along, it was me or your Math 20 teacher, Mr. Hetlinger maybe, who said, you know what, you need to go plus or minus, and we would explain why. Maybe we would have said, if I have, forgetting about x and y, if I have a squared equals 16, a is equal to 4, but a can also be equal to negative 4, because when you square negative 4, you also get 16. So that's why we would write a equals plus or minus root 16. This plus or minus was new. Let's keep that in mind as we move forward. So, and by the way, this is called the quadratic function. The inverse is a square root function. If we look at, just as an example, and there are a lot of different exponential functions I could use here. I could have used 0.5 to the x. I could have used y equals 10 to the x. But I'm going to stick with y equals 2 to the x. The inverse of this exponential function is called a logarithmic function. And the inverse would be what we get when we switch x and y. So when we look at y equals 2 to the x, we call that an exponential function. When we look at x equals 2 to the y, we call that a logarithmic function. How do we rearrange that for y? Well, you can't. It would be like me saying, how do we communicate that the answer could have been the positive square root or the negative square root? You had to be given a new symbol or a new way of communicating it that was unfamiliar to you. So instead of writing x equals 2 to the y, we write this. We write y equals, and it's pronounced, a couple of ways we can pronounce it, y equals log base 2 of x, or y equals the base 2 logarithm of x. So this is going to get muddy. These two expressions are not the same. They are inverses of each other. The one on the left is the exponential function. The one on the right is the corresponding logarithmic function. But since we can write x equals 2 to the y as y equals log base 2 of x, these two things that you're looking at now on the bottom of the screen are the same. X equals 2 to the y is like y equals log base 2 of x in the same way that bonjour is like hello. They are the same thing. So if you ever see y equals log base 2 of x, you should know that it means x equals 2 to the y. I want you to notice something here, because you're going to have to be able to translate these. And again, don't worry about your calculator right now. Worry about what I'm saying. In both of these expressions have a base. There's a base of the exponential function, which is 2, and there's a base of the logarithmic. So it's the same base in both. If you have a base 5 in the exponential function, then when you translate it to the logarithmic function, it's going to be a base 5 as well. I want you to notice that in the exponential function, one of the variables is by itself. But when you translate it to the logarithmic, it's the other variable that's by itself. So the x is by itself in the exponential, the y is by itself in the logarithmic. We can go even further and say that the argument of the exponential function, remember the argument in mathematics is the thing that you're operating on, the thing that you're raising to the 2. In this case, the argument is y in the exponential, but in the logarithmic, the argument, the thing that you are, this is just my way of saying it, the thing that you are base 2 logging, the thing that you were taking the base 2 logarithm of, is the other variable x. So, and we're going to come back to that, but we want to make this more general. If I have y equals c to the x, looking at the middle of the screen here, and I have y equals log base c of x, these are inverses. And I want to dissect this for you. We'll get to all those details at the top of the screen in a second. If you didn't know that the inverse of y equals c to the x is y equals log base c of x, which I hope you do eventually catch on to that, you would say the inverse of y equals c to the x is x equals c to the y. Okay, by switching x and y. But then you would say, how do I write this as y equals? And you would say, since this is the exponential function and it's x equals, the logarithmic function will be y equals. The argument in the exponential becomes the lone variable in the logarithmic. And then you would say it's a logarithm, and it's the same base as the exponential, so it must be the log base c of x. So one way or another, you need to know that y equals c to the x and y equals log base c of x are inverse operations. Let's take a look at the details at the top of the page. It's got all these conditions. X is greater than 0. C is greater than 0. C is not equal to 1. Well, I want to point out to you that these two statements are true for the same reason that they were true when we talked about exponential functions. The base of an exponential function, if you look on the left, this is an exponential function. The base has to be a number greater than 0, and it can't be 1. That's that line that we included in our notes where you said it couldn't be 0, it couldn't be 1, but it could be any value in between 0 and 1 and any value greater than 1. Now, why does x have to be greater than 0? Well, let's say x was negative in this expression here. Okay? In this expression, and this is going to get a little muddy as well, in this expression, if x equals, say, negative 10, okay, and it doesn't matter what c is and what y is, we'll get to that in a second, then this would become y equals log base c of negative 10. And what I'm telling you is that is not allowed. Okay? When we say x is greater than 0, we are telling you that you cannot take the logarithm of 0 and you cannot take a logarithm of a negative. But what does this mean? Well, I am going to tell you, and this is the advice I'm going to repeat again and again, that if you are looking at some expression, like say this one, and it doesn't make sense to you, you don't understand what it is it's telling you, translate it to the other language. Let's write this in exponential form. So if I write this in exponential form, then this argument goes by itself. And it becomes a base c exponent of the other piece. And I can tell you this right now, you will get a visual that when you convert a logarithmic to an exponential, what you're going to be doing is taking this and raising it to that and setting it equal to the argument. Okay? But when you translate this logarithmic expression here to the same idea here, these are not inverses. I've just translated it to a different form. I've rearranged it. This is saying c raised to some number is negative 10. But c is a positive number. Remember that c, for exponential or logarithmic, can be anything between 0 and 1 or greater than 1, but it cannot be equal to 0 and it cannot be 1. But in the end, it's a positive number. So this idea is saying that you have negative 10, which is going to be equal to a positive number raised to some value of y. Well, that would never happen. You cannot raise a positive base to something and get a negative. And what I want to highlight for you in terms of a summary here of this discussion about x in the logarithm is you just can't take the logarithm of a number unless it's greater than 0. In fact, you do have a log key on your calculator, and I know that you're still unsure about what this is all about, but let's try taking the logarithm of 0, just for kicks. There's a log key here, log. It means something more specific than what we've been talking about, but if I try taking the log of 0, well, the math gods slap me on the hand. They tell me that it's not possible. If I try taking the log of a negative number, same thing. Don't worry about the exact meaning of the error. I think one said domain error and the other said non-real answer. It's unimportant. But if I take the logarithm of, say, 100, I get 2. I get a number. Logarithm of 100 is defined. Don't worry about why it's 2, but at the end of the lesson you should know why it's 2. All right, so just a reminder here that your textbook uses C for the base, but we tend to use B on the formula sheet. Let's graph y equals 2 to the x and y equals log base 2 of x on the same set of axes. How are we going to do that? Well, I've got a table of values here, but I don't know that you need to write down the table of values. You can if you like. What I would say to you, everybody, is you should know how to plot the points for y equals 2 to the x right now. You should say that y equals 2 to the x has a y-intercept of 1 with a growth rate of 200% because the base is 2, which means that every time you go 1 to the right, you double the old y-coordinate. So we move over 1, it doubles to 2. We move over another one, it doubles to 4. We move over another one, it doubles to 8. You could certainly figure out those coordinates by taking, say, 2 to the 0 and getting 1, and 2 to the 1 and getting 2, etc. But I'm saying these points should be like family to you. They should be very familiar. You should know where they are. And if we wanted to, we could go in the opposite direction and divide by 2. And I don't want to push it. I would divide by 2 again to get a quarter at negative 2. I think that's getting too close to the axis. We do know there is a horizontal asymptote. And this graph, if you want to risk it, you can draw the curve. If you're shaky because you're naturally shaky in drawing stuff or you've had too much coffee, you don't have to draw it. You do need to understand there is a smooth curve going through it. I'll do my best. Sometimes I have a combination of natural shakiness and caffeine overload, but that's not bad. So this is y equals 2 to the x. Now, just think about this for a second. If y equals 2 to the x looks like that, and y equals log base 2 of x, the other graph, the other function that we're asked to graph is the inverse, that means everything about x and y swap. So if there was a horizontal asymptote on the x-axis, then for the logarithmic function, there'd better be a vertical asymptote on the y-axis. Let's just keep that in mind. Now let's physically take some points and swap them. So for example, and I don't know if you want to maybe use scrap paper here or just write things down, or maybe you can remember these things. But for example, this point here is at 3, 8. Now some of you might need to actually write someplace 3, 8 down so you can visually say, oh, it's going to be 8, 3. If you don't have to, you don't need to. But 3, 8 is going to map to 8, 3. 2, 4, on the original graph, we switch x and y because this is what happens with an inverse, becomes 4, 2. One, 2 would become 2, 1. By the way, if you want, you can make a note that this is a beautiful reflection in the line y equals x, which it had better be because that's also a way we could arrive at an inverse graphically. 0, comma 1 becomes 1, comma 0. And this again is reinforcing the idea here that everything true about y becomes true about x, because on the exponential function, y equals 2 to the x, the y-intercept is 1. So on the inverse function, the x-intercept better be 1. And the inverse function is, and I'm just going to write it here right away, y equals log base 2 of x. The point on the left at negative 1 on y equals 2 to the x is at negative 1 comma a half. So if we swap the x coordinates, it will be at half negative 1. And just as moving to the left on the exponential function, the curve is going to get smaller and smaller and smaller vertically, approaching the x-axis. Going in a negative direction for y, it's going to approach the y-axis for the logarithmic. So the logarithmic function looks like that. And there is an asymptote. It's a vertical asymptote. So that's what they look like. You're expected to know what the graph of y equals log base 2 of x looks like. And some of you will just take a mental snapshot of that graph, and you will know. I'm never comfortable just drawing it. I'm never comfortable standing in front of a class and saying, okay, we need to look at the graph of y equals log base 3 of x. Here's what it looks like. I would much rather take a moment and sketch y equals 3 to the x and swap out some points to get a good picture. Because if the base is between 0 and 1, your exponential function, please don't draw this, but if the base is between 0 and 1, your exponential function will look like this. Which means your logarithmic function is not going to look the same as what we drew it. And I'm telling you, I have to physically start mapping some points by switching x and y on some known points to get the corresponding inverse of that. Okay, so complete the following table. What is the domain of 2 to the x? Well, you should have a visual in your head of what y equals 2 to the x looks like without even looking at the graph that we drew. The domain is x is any real number. I'm not going to worry about color coding things here. And the range is y is greater than 0. We don't need to look at the graph of y equals log base 2 of x to answer domain and range for it. All we need to know is that it's the inverse of y equals 2 to the x. So everything that was true about y, for example, on the original function y was greater than 0, becomes true about x on the inverse. And everything that was true about x on the original, namely that the x variable on the exponential was any real number, becomes true about y on the inverse. You should probably know, without looking at, without having to construct the graph, you should probably be able to visualize y equals 2 to the x in your head and say there's no x-intercepts because the x-axis is a horizontal asymptote. That would mean that there are no y-intercepts on the inverse function. You should know that the y-intercept of y equals 2 to the x is, let's go whole hog here and actually write it as an ordered pair, is 0, 1. I don't really like at this level just saying y-intercept equals 1. I'd rather say 0, 1. That means the x-intercept is 1, which is 1, 0. The asymptote, this is the x-axis for the exponential function, which has an equation of y equals 0. That means the vertical asymptote will be the y-axis on the inverse of that function, which has an equation of x equals 0. Any questions with that example? All right. So this next big idea is very important. What a logarithm is an exponent. Okay, and the language I'm going to use here is very important. A logarithm is an exponent, and I'm going to be spending the rest of this lesson working with you in converting from logarithmic to exponential and understanding these things. And at many times I'm going to say, well, wait a minute, the logarithm is the exponent. That's how we're going to solve these problems. So I've already talked about this. If you take a look at this first statement, the exponential function y equals c to the x can be written as x equals log base c of y. I want everybody to roll this around upstairs in your head. And I've talked about this a few times. I'm translating y equals c to the x to logarithmic. So when I look at y equals c to the x, y is by itself, which means the equivalent. This is not an inverse. These two things are not inverses. They are the same thing, written in a different language. If y in the exponential is by itself, then x in the logarithmic equivalent is by itself. And the base is the same for both, and that means that if x is the argument of the exponential, meaning it's what you are operating on, if x is the argument in the exponential, then y must be the argument in the logarithmic. How many of you are starting to get a feel for rearranging this? Okay. Well, what if I had this? What if I had y equals log base c of x, which is not the same as anything that I've highlighted in blue? And I said rearrange that for x. Well, you would say that x is c to the y. And I guess what I'm saying is you need to be able to translate from exponential to logarithmic or logarithmic to exponential regardless of what the variables are or where the variables are. So, as an illustration, if I said, what is this in logarithmic form? It would be x equals, and it would be log base c of x, or log base c of y, rather. If I said rearrange y equals log base c of x for x, you would have to write it in exponential, and you would say x equals c to the y. If I said rearrange this, p equals log base q of r, I want you to write down what r is equal to right now, someplace. If you can write it down in your head and remember it, then that's fine. What would r be equal to? Q to the p, right? Doesn't matter what the stuff is. If I had duck equals fish to the moose, remember my philosophy on math is all this stuff we write and we use rules around are just squiggles on paper. I mean, they mean things, obviously. We're not just randomly writing stuff down. But it's all symbolic. Math is a symbolic language. So if I had duck equals fish to the moose, and I said, go ahead and write that in its equivalent logarithmic form, what would you write? Should write it down. And you may need to actually write it down. I know some of you can just look at this and go, I know, I get it. But remember, you only have access to how you're thinking. You have no idea how anybody else in the room is thinking. Moose equals log base fish of duck. The base is the same in both. If the exponential function has a base of fish, then the logarithmic will have a base of fish as well. Remember, these are the same. These are not inverses. We did not switch the two variables. We're just rearranging. Duck was by itself in the exponential. Moose has to be by itself in the logarithmic, which means the arguments switch as well. All right. When I started off the introduction to this, and I talked about, I think in the seminar, it's not a long lesson, but the concepts are deep. This is what I'm talking about. We should, with a good foundation now, be able to burn through all these examples relatively quickly. Convert each of the following from exponential to logarithmic form. So the base is 4. That means it's going to be a log base 4 operation, or a base 4 logarithm. So the word log is written on the main line of where you write stuff, and the 4 is a subscript. The argument in the exponential was p. We were operating on p. We were raising p to the 4, which means the argument on the corresponding logarithmic statement will be log base 4 of n, and then it becomes p. And this is what I mean when I say a logarithm is an exponent. This logarithm is equal to p. And p is the exponent to which you raise 4 to get n. So the logarithm is always equal to the exponent. The exponent in the exponential function becomes what the logarithm is equal to in the logarithmic. This would be log base 2 of 1/32, and it's equal to -5. Now be careful here. I told you you cannot take the logarithm of a negative, and that's true. But that doesn't mean a logarithm can't be negative. Why is this true? Because 2 raised to the -5 would give you 1/32, 1/32. Whenever you take the logarithm of an argument that's smaller than 1, you're going to get a negative number. Any questions with A or B in example 2? I just want to make sure that's all there was in example 2, A and B. Okay. Convert each of the following from logarithmic to exponential. Well, the base raised to the argument, the base raised to the new argument will be the base raised to the item that was by itself. 10 to the 2 equals 100, which is true. How many of you are just getting used to the idea that it's the base raised to the other side equals the argument of the logarithm? I hope that's kind of where your brain is going. So this would be x raised to the m equals k. You don't want, this has to be so obvious. Bonjour. Oh, the person's saying hello. You have to be able to switch back and forth. We cannot rearrange this for an exponential form yet because of that coefficient of 4. So what we would want to do is divide both sides by 4 to begin with and get log base b of 9 equals 4. And now we can write, b to the 4 equals 9. Any questions with 3? I want everybody to figure out what log base b of 1 is. And I know I'm just kind of throwing you out into the wild and saying survive, figure it out, but I want you to see if you can figure it out. How many of you know almost immediately what it's equal to? That's not surprising that nobody does. So how could we do this? Well, what we could do, and this is just an idea, is we could say, well, if we want to find out what that's equal to, why don't we set that equal to A? A stands for answer. And let's write it in exponential form, because nobody in the room understands that logarithm yet. So let's translate it to a language we're more familiar with. And I would write this as b to the a equals 1. Don't forget, we are trying to find the value of a, because a stands for answer. A is what this is equal to. So the question is the following. What number would you put up here so that when you raised that as a power of a base, you would get 1? Jason? 0. It's 0. Log base b of 1 is 0. And now I'm going to tell you that I wouldn't do it the way I've done it by putting a up here. I would have simply said this. What is a logarithm? A logarithm a logarithm is an exponent. So log base b of 1 is the exponent to which you raise b to get 1. What do you raise b to get 1? 0. And what you're kind of doing is you're kind of saying, what is this exponent that I'm raising b to give me this argument? You are kind of rewriting it in your mind as b to the answer equals 1. But you're simply saying, what exponent do I raise b to get 1? That's what log base b of 1 is equal to. So what is log base b of b? Log base b of b is saying, to what do I raise this green b to get this red b? To what do I raise b to get b? It seems like kind of an insane question, but the answer is 1. This is equal to 1. I don't like that we don't often put brackets around there, but we probably should. The argument here is b to the n. So listen very carefully. Log base b of b to the n is saying, to what do you raise b to get b to the n? It's saying, to what do I raise b so that I get b to the n? N. B to the n is b to the n. Again, kind of a weird question, but that's why this is equal to n. And everything we've done so far has nothing to do with your calculator. I keep seeing some people going back to their calculator. I don't think it's going to help you right now. I know you want to move forward, but I also don't want you to get lost. Log base 2 of 64. Log base 2 of 64 is saying, to what do you raise 2 to get 64? I want to actually write that down. To what do you raise the base of 2 to get 64? That's what log base 2 of 64 is equal to. And you know, at this point, I would rather you just play around with your calculator and figure it out. 2 to the what? Because some of you have calculators that you can enter in log base 2 of 64, and it will spit out the answer of, I believe, 6. Is it 6? But I don't want you, if you've discovered that already, I don't want you doing that. You're really saying this. 2 raised to something is 64, and this goes back to what we did yesterday with common bases. You could, if you wanted to, solve this by converting everything to a common base. But I don't think you actually need to do this to know that the answer is 6. So you would drop the bases now and say it's 6. To what do you raise 6 to get 1/36? Now, how many of you know the answer? Okay. Most people won't. A few people put their hands up. So if you don't know the answer, and hopefully you will later when you see something similar, you would revert to what we learned yesterday. You would solve this exponential equation where x is the answer. Can I write these two things with the same base? Yes, base 6, because 36 is 6 squared. Now, it's not quite at the stage where I can drop the bases because I have 1 over, but I can write this as 6 to the x equals 6 to the negative 2, which means log base 6 of 36 is negative 2. Is that what you thought? Okay. Ben, is that what you had in your head? Okay. What about log base 2 of 8? Again, one that I would like you to just think about. Let me give you a few seconds to let that percolate in your brain. what this is saying, and everything I'm writing here, this is all just kind of scrap paperwork. And what I'm telling you is you should be able to come up with these answers without actually doing a lot of work on paper. How many of you know what the answer is here? You're pretty sure. Okay, Jason, do you know? 1/3. Perfect. Can I ask how you got that? Okay, so guess and check. But it was an intelligent guess and check, right? You knew the number 3 had to be involved because 2 cubed is, but you knew it was a fraction. If you wanted to, what you could do is say, what power do I raise 8 to get 2? Well, you notice that the cube root of 8 is 2, and that means 8 to a power of 1/3 is 2. Did anybody think of it that way? A couple people. You could, instead, say that 8 to the x equals 2, and 8 is 2 cubed, so now you have 2 cubed to the x is 2 to the 1, and then you have 2 to the 3x equals 2 to the 1. The bases are the same. You equate the exponents. How many of you did it that way? A couple people did it that way. So there's an intuitive approach like Jason. There's a couple of different algebraic approaches here. Here you're going to get 3x equals 1, so x equals 1/3. All right, example 5. We do have a logarithm button on the calculator. It just says log, but it's base 10. And you need to know that from now on, when you see something like log of 10,000 and the base is not written, there should be a base here, but it's not written. It's called the common logarithm. And what's the most common number in our numerical number system? 10. We like to use 10. Everything's base 10. So what is log of 10,000? That's saying, what is log base 10 of 10,000? And that is saying, to what do you raise 10 to get 10,000? Well, 10,000 has 4 zeros, so 10 times 10 times 10 times 10 would give you 10,000, and this gives you 4. We won't calculate it just yet. What is log of 0.001? Well, 0.001 is 1 over 1,000, or 10 to the negative 3. So this must be negative 3. Negative 3 is the exponent to which you raise 10 to get 1 over 1,000. You could certainly check these now on your calculator. Log of 10,000. Well, look right above what I have here. Remember I typed in log of 100 and I said, well, it's equal to 2? Well, it's equal to 2 because 100 is 10 squared. Log of 10,000 is equal to 4 because 10 to the 4 is 10,000. Log of 0.001, negative 3. Number 6, estimate each of the following. What we're really trying to do here, and this is how it would appear on an exam, is you're trying to find two numbers that this is between. You're really trying to find two numbers, two whole numbers in this case, that log base 3 of 50 is between. So what we start doing is we start off by saying log base 3 of 50 is saying, to what do you raise 3 to get 50? So let's narrow it down. 3 squared is 9. 3 cubed is 27. Am I right? 3 cubed is 27. What's 3 to the 4? 81? Okay, we're looking for 3 to an exponent equals 50. 50 is between 27 and 81, which means that log base 3 of 50 is between 3 and 4. It's some number between 3 and 4. I don't care what that number is. You know, could you start playing around on your calculator and saying, let's try 3 raised to the 3.5. Ooh, that's almost 50. Let's try 3 raised to the 3.6. Could you walk down that road? Sure. It's not worth our time, though, because later on you will know how to evaluate that exactly. Log of 250. Well, this is base 10. So we are looking for just kind of a domain of values. I'm using domain. I don't know if that's an appropriate word. What are two integral values, or whole number, or natural values in this case, that log base 10 of 250 lies between? Well, that's saying, to what do you raise 10 to get 250? 10 squared is 100, 10 cubed is 1,000. It must be between 2 and 3. So what I'm writing here is the answer to the question. The estimate of log base 10 of 250 is it lies between 2 and 3. This we could, of course, calculate, because we do have a log base 10 key. We don't have a log base 3 key, so we can't calculate what A is equal to. But I can calculate what log of 250 is. It's 2.4, approximately. Any questions with that? Okay. Final example. We have to determine x in all of these. Log base 3 of 27 is equal to x. You don't know it, but you're solving a logarithmic equation right now, in a way. I want you to figure out what x is. And my hope would be you just know the answer. But you look at that and go, oh, it's asking me to what do I raise 3 to get 27? And the answer is 3 raised to the 3 is 27. So log base 3 of 27, which is equal to x, is equal to 3. If you like, you might look at this and be confused. Maybe. I hope not. But then you remember that Mr. Way said, if it's confusing in one language, rewrite it in the other language. And when I rewrite this in exponential form, it becomes 3 to the x equals 27. And that might be more of a visual clue to you that x has to be 3. But my hope is when I say, quote, to what do you raise 3 to get 27, you understand that I'm really just saying that, aren't I? But I'm saying it in my head, or verbally as opposed to writing it. Log base 27 of 3 equals x. And it's certainly okay to verify things with your calculator, but intuitively you should say this is a third. That's the intuitive nature. I can't teach an intuitive nature for this particular solution to you, but anytime your argument is a smaller number than the base, you're going to get a negative answer, or you're going to get a fractional answer. Okay. If I write 27 to the x, which is the language I can become more familiar with, equals 3, then I can write 3 to the 3x equals 3, and that's 3 to the 1. Are you okay with me saying 27 to the x is 3 raised to the 3x? It's really, I maybe shouldn't have done that, but it's 3 raised to the 3 raised to the x, which gives you 3 to the 3x. 3x equals 1 then, because the exponents must be equal if the bases are equal. So you divide both sides by 3, you get a third. I've never really figured out a way to explain why intuitively that makes sense to me, other than to say you have to take the cube root of 27 to get 3. And a cube root as an exponent is an exponent of a third. Log base x of 81 equals 4. Well, see if you can figure it out. This is not asking you to find the exponent. You know the exponent. Put your hand up and then down if you know the answer. And then continue to, that's everybody basically. It's 3, isn't it? This is saying, what do you raise to the 4 to get 81? And this is really a polynomial equation. And the answer is going to be 3. Because the 4th root of 81 is 3. Now, we're okay with the answer here being 3. Does anybody have any questions with that? Technically, since this is an even exponent, it should be plus or minus 3. Okay? Or you could solve it by factoring this after subtracting 81 from both sides, factoring it as a difference of squares, continuing to factor it, and seeing that there are 2 zeros of this polynomial equation, -3 and 3. Why do we kick -3 over the boards? Ben? Say? Thank you. Yeah. And I was going to ask, what do you mean by x? The base cannot be negative. The base has to be a positive number, not equal to 0 and not equal to 1. So we kick that one out. Figure this one out for me, please. Log base 5 of x is equal to 3, and we want to find x. Hand up, then down if you know the answer. So if you're confused by this, you write it in exponential form. And this shows the importance of being able to translate from one language to the other. It should be, like, without much thought, you should know that log base 5 of x equals 3 means 5 to the 3 equals x. Well, there you go. 5 to the 3 is 125. So x is 125. Log base 1/2 of 32 is equal to x. Might require a little more thought. But hand up and down if you know the answer, like almost immediately. So fewer hands this time, right? It's not entirely obvious. Continue to put your hand up and down if you got the answer, but you didn't put it up and down before. So I hope you're not poking around on the calculator trying to find it. What you should be doing is saying, learning from yesterday, that 1/2 can be written in base 2, 32 can be written in base 2. On the left-hand side, I have a power of a power, which means I can multiply the two exponents. And I end up with comparing the exponents -x equals 5, so x equals -5 when I multiply both sides by negative, or divide both sides by negative, or switch the sides of the equation. So, don't forget, you do need to know how to find out what the graph of a logarithmic function looks like. I don't really like this graph. It's a little too bold for me, but it's from your textbook. We're going to be building on that tomorrow. The most important thing is that you are able to convert y equals c to the x to log base c of y equals x, where these are the exact same thing. Whole slew of suggested practice problems for you to work on. You've got about 20 minutes here left in class today.